2, none, none. Or I could have 1, none, 2. Sorry. 1, 0. Because that corresponds to 2 HDIs, and this would be 1, so that's 3. Right? And I'll go to 0. So 0, and I could have 3, 0, 0, and so on. So I want you to complete this for me. Okay. But here's the point I wanted to make. This is not some kind of magical, voodoo sort of thing here. If I tell you that a Coke costs $1, a Pepsi costs $1, an orange juice costs $2, and a protein shake costs $4. Right, so that's the menu in the convenience store. A Coke and a Pepsi at the same price, $1. An orange juice is $2, and a protein shake costs $4. Okay, good. If I give you $0, and I say go to the store and buy a drink, tell me, what can you get for $0? So here's my Coke, here's the Pepsi, here's the orange juice, here is the protein shake. If I give you $0, you can buy none of those. Right? What if I give you $1? Well, with $1, you can buy a Coke. But once you bought the Coke, you can't buy anything else. Or maybe you can buy a Pepsi. But if you buy the Pepsi, you can't buy anything else because you only had $1 to spend. If you have 2 HDIs to spend, $2 to spend, and I send you to the store, what can you get with $2? Well, for $2, you can get 2 Cokes. Once you spent that, you can't get anything else. You can get a Coke and a Pepsi, nothing else. You can get 2 Pepsis, nothing else. Or maybe you can get an orange juice. Right? So it's nothing strange, right? You have a certain number of HDIs to spend. Each structural feature, double bond ring, triple bond, benzene ring, costs a certain number of HDIs. I give you a certain number of dollars to spend. Each drink costs a certain number of dollars. You can only spend what you have. If I give you $3, what can you buy? 3 Cokes, nothing else. 2 Cokes and a Pepsi, nothing else. 1 Coke and 2 Pepsis, nothing else. A Coke and an orange juice. I could have also gotten a Pepsi and an orange juice. Or I could have bought 3 Pepsis and blah, 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 blah. So what I want you to do for me is to go through, is to do this for table 3, for 3 HDIs, and there are more options. Do it also for 4 HDIs, right? And just work that through. The last thing we do before we finish is to ask the question, which was the first question we had, which got us into this discussion. This is all well and good if my compound is a hydrocarbon, right? If the only elements I have are C and H, this is perfect. All I do is I look at the formula of my hydrocarbon, compare it to the formula of the corresponding alkene, see how many H's are missing, and we are good to go. We can work out our HDIs, right? So, for example, if I have if I want to draw C5H8 or C6H10, and I say draw 3 isomers of this, of each, let's say. That's easy. C5H8, I'm going to compare that formula to the corresponding alkane. The alkane, CnH2n plus 2, with the same number of carbons, 5. So this will be C5H, 5 times 2 is 10 and 2 is 12. I am missing 4 H's. 4 H's is tantamount to 2 pairs of H's. This is my HDI. So now, knowing that, with 2 HDIs, I can either have 2 double bonds, double bond in a ring, 2 rings, or a triple bond. Let's just pick one of each. So I can have 2 double bonds. I'm going to go ahead. I can either have these. This is where the beauty comes in. I can have all 5 in a row, or I'm going to be cheeky and put them like that. So I'm going to put so 2 double bonds. I'll go 1. What the heck? 2. So 1, 2, 3. 1, 2, 3, 4. Nope, can't go there. Right, this already has 1, 2, 3, 4 H's. So 1, 2, 3, 4, 5, 6, and then up here 7, 8, and we're done. That's one isomer. And anything you draw that obeys the structural theory that has the 2 HDIs is correct. You could have drawn the carbons all in a straight line. So that's 2 double bonds. So I want 2 rings. So I can say C, 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 C. That's 1, 2, 3, 4. 5. That's 2 rings. 1, 2, 3, 4, 5. In which case I have 1, 2, 3, 4, 5, 6, 7, 8 H's. So that's 2 double bonds, 2 rings. I could have a ring and a double bond. And I'll make this one a 5-membered ring. And I'll put a double bond here, for example. And you could have done a 4-membered ring with a 1-carbon appendage, a 3-membered ring with 2 1-carbon appendages, or a 2-carbon appendage. All would have been right. Put in my H's. 1, 2, 1, 2, 1, 2, 1, 1. So 1, 2, 3, 4, 5, 6, 7, 8. Let's do just I know this is good enough. Let's do just to show you the whole concept of complexity. I could have had a 3-membered ring with 2 1-carbon appendages, either on adjacent carbons, here and here or here and here, or the 2 1-carbon appendages on the same carbon. Okay? Or I could have done a 3-membered ring with a 2-carbon appendage. All of those are options. And then put a double bond as well. The double bond here could be in the ring, that's one position. In the ring, endocyclic, that's a different position. In the ring, that's another position. That's 3. Or it could have been exocyclic. Here or here would be the same. Right? So complexity emerges. Double bond here or here. Or here or here. Right? Couldn't put a double bond here, but I could put one here. Right? So let's just underscore the number of options. So 2 double bonds, 2 rings, a regular double bond, or a triple bond. And I'm just going to be lazy and go C, triple bond C, and then I'm going to put all my carbons, 1, 2, all my carbons here, and that will be fine. So 1, 2, 3, 4, 5, 1, 2, 3, 4, good God. 1, 2, 3, 4, 5, put H, 1, 2, 3, 1, 2, 3, none, 1. So 1, 2, 3, 4, 5, 6, 7, 8. It has to work out. If you find it doesn't work out, it means you've done something wrong. Either you have the wrong number of carbons, or you haven't paid attention to the number of indices of hydrogen deficiency. Okay? All right. Okay, so I'm going to leave this one alone. Okay, so what if you have a case that has heteroatoms. How do we handle those? And the answer is really quite simple. It depends upon which group the heteroatom is in. So I'm going to erase this, and I know you guys can rewind and so on, so I'll let you take care of that bit. You can rewind and pause as is necessary. So let's go ahead and see how we handle cases where we're dealing with heteroatoms. And the best way of doing that is to imagine that we start off with methane. Methane is our simplest organic compound, and that is CH4. So what I'm going to do is I'm going to take methane, and I am going to replace one of the H's in methane by an atom that is monovalent, like a chlorine, for example, an atom that is divalent, and an atom that is trivalent. So if I replace this by a monovalent, let's say chlorine, I'll have C, H, 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 and Cl. And that formula is CH3Cl. If I replace it by, I'm replacing an H now, by a divalent, like oxygen, I'll have CH3O. But I want to make sure the compound I make is reasonable, so I have to fill the valence of the O with an H. And that is CH4O. I'm going to replace it now by a trivalent, and that's going to be CH3, and then an N, and I'm going to complete the valence of the N with H's. And this formula is CH5N. So let me just again be clear on what we're doing. We are substituting one of the H's in methane systematically by an atom that is monovalent, chlorine, group 7, so the valence is 8 minus 7. A divalent, like oxygen, which is in group 6, so the valence is 8 minus 6, which is 2. Nitrogen, which is trivalent, so the valence, and in group 5, so the valence is 8 minus 5, which is 3. And I want to make sure I complete the valences with H's. Okay. Now I'm going to ask, what do I do to each of these formulas to bring it back to CH4, to repair it? And the answer is, when there's a monovalent, I'm just going to add one H for every monovalent. So if I replace this Cl by an H, if I add an H for the one Cl, I'm back to CH4. If it's a divalent, I'm just going to ignore it. Because if I ignore it, I'm back to CH4. If I'm a trivalent, I will subtract one H for every trivalent atom. So for monovalent, add an H. For divalent, do nothing. For trivalent, subtract an H. Good. So for C3H6O, how do we handle the O? And the answer is, we ignore it. So that is basically C3H6. I'm now going to compare that formula to the corresponding alkane, Cn, seriously, CnH2n plus 2, that has the same number of carbons, 3. This will be C3H8. So now I'm missing two H's, which is one pair of H's. That's my HDI. So if you remember when we started this topic, I said if I've got C3H6O, I'm just going to draw my skeleton out and then try to fix the H's on. I think I had done a CCCO, and then got 1, 2, 3, 4, 5, 6, and realized something weird was happening. I don't have to do that. I know one HDI means I have either one double bond or one ring. So I'm going to put those in before I start. I'm going to say, look, I'm going to have my three, I'm going to go CCCO, for example. But I can make that so there's a double bond here, or a double bond here, or a double bond here. Right? I can do that. So I can, why don't I do the third one? So CCC, double bond. Or there could be a ring. And the ring could either be CCCCO, or I could have, I could have CCCO, or I could have CO with a C. All of those are possibilities. So I know that going in. So I've got my 3 carbons, 1 O, and 1 HDI. Double bond, I don't care whether it's CC, here or here, or CO. Doesn't matter. 1 ring, I don't care what the size of the ring. All I have to do now is plug the H's in, and it must work out. So complete the valences. 1, 2, 3, 4, 5, 6. We're good. 1, 2, 3, 4, 5, 6. Nothing here. We're good. 1, 2, 3, 4, 5, 6. Nothing here. We're good. 1, 2, 3, 4, 5, 6. We're good. 1, 2, 3, 4, 5, 6. Nothing here. We're good. And there's no mystery. So when you're given the molecular formula, the first thing you do in any question, and this will happen in organic 1 and organic 2, the first thing you do, because the molecular formula gives information, we said that yesterday, the first thing you do is you work out the index of hydrogen deficiency, so you are armed with which structural features you're allowed. And if the question doesn't give you any details as draw C3860 that has a carbon-oxygen double bond, if it tells you nothing other than draw isomers, pick what you want and draw it. And as long as you obey the structural theory, you're good. Any answer, every answer is correct. Now, let that soak in for a second. Even with C3860, and we haven't done them all, any structure you draw that obeys the structural theory is valid. So think about it. How many organic compounds must there be? With only C3860, look at how many we got, and we're not finished yet. Imagine C10, or C20, or C100. And the gravity of the situation in terms of the sheer number of organic compounds is going to start to make an impact. Okay, so we'll stop there, and I'll see you guys on Thursday. Thanks. Study hard.